We now start chapter 3 module 6 and we will continue with determinants. We will first study some very important properties of determinants. We have already seen some of them in the previous module, but here we will see a different listing, and then we will learn a very useful theorem called the Cramer's rule, which gives a computation of a solution of a system of linear equations. And finally, we will introduce n-linear maps and alternating maps and settle that characterization of determinant function, and that would settle a question that we raised in the previous module related to determinant representing area of a parallelogram up to a sign. Let us start. F denotes a field. Let us first talk about determinants of elementary matrices. We recall that there are elementary matrices of three kinds, and that are obtained by applying three kinds of elementary row operations on the identity matrix. They are given by the type 1 is the one which is obtained by interchanging any two rows of the identity matrix. Type 2 is the one obtained by multiplying some row by a non-zero scalar alpha, and type 3 is the one obtained by adding a multiple of some row of I to another row. And then it is easy to see that for type 1 determinant will be -1, for type 2 determinant will be that scalar alpha, and for type 3 the determinant will be 1. The listing of the determinants for elementary matrices for type 1, 2 and 3. Let us now prove this theorem, which says that determinant function is multiplicative. That means determinant of AB is determinant of A times determinant of B for every n cross n matrices A and B over F. So, let us assume first that A is an elementary matrix of type 1, then AB, the product, is the matrix obtained by interchanging two rows of B. We know that if we pre-multiply by an elementary matrix, then that amounts to an elementary row operation on the matrix B, and therefore we have interchanging two rows of B when we multiply B by that elementary matrix A from the left hand side, and that gives us determinant of AB is equal to minus of determinant of B. But we know that A being elementary matrix of type 1, determinant of A is -1, and that proves this multiplicative property. By similar arguments, we can establish the result for A and B, where A is an elementary matrix of type 2 or type 3. Now, let us assume that rank of A is less than n. That means rank of A is not the full rank. Then we know that determinant of A must be 0. Moreover, rank of AB is less than or equal to rank of A, and that is less than n, and therefore determinant of AB is also 0, and that proves the multiplicative property for the det function under this condition. Now, suppose that A has rank n, then we know that it is invertible, and it was proved before that A can be written as a product of elementary matrices, let us say EM, EM minus 1 and so on up to E1, and therefore determinant of AB is determinant of EM, EM minus 1 and so on, E1, B. We have already proved the result when A is elementary matrix, we apply that here with EM, and therefore we get this is equal to determinant of EM times determinant of EM minus 1 and so on up to E1 B, and then we do it in an iterated fashion, and finally what we get is that determinant of EM, EM minus 1 and so on up to E1 multiplied by determinant of B, but that product what you see over there EM, EM minus 1 and so on E1 is nothing but A, and therefore we have determinant of A times determinant of B. So what we see here is that the elementary matrices once again play a very important role when we are talking about properties of determinant, especially for matrices which are invertible can be written as product of elementary matrices, which is being used here and which will be used again. Corollary: a matrix A in M and F is invertible if and only if det A is not 0, and if A is invertible then det of A inverse is 1 over det A. Proof: if A is invertible then A inverse exists, and A inverse is I, and by the multiplicative property of determinant we get determinant of I, that is 1, and that is the same as determinant of A times determinant of A inverse. Therefore, determinant of A cannot be 0 and determinant of A inverse is 1 over determinant of A, and if A is not invertible then rank of A is less than n, determinant is 0. Now another very important property which says that determinant of A transpose is the same as determinant of A for every A in M and F. Proof: suppose that A is not invertible, then rank of A is less than n. We know that rank of A transpose is equal to rank of A, and therefore A transpose is also not invertible. This proves that determinant of A transpose is equal to determinant of A is equal to 0. So this result is therefore proved now under the assumption that A is not invertible. Now assume that A is invertible. Once again you see that the elementary matrices are being used. So A can be written as a product of elementary matrices given by EM, EM minus 1 and so on up to E1, and determinant of EI transpose, it is determinant of EI for the elementary matrices. Therefore, determinant of A transpose is determinant of E1 transpose, E2 transpose and so on EM transpose, and then we apply the multiplicative property of determinant and we get determinant of E1 transpose times determinant of E2 transpose etc. up to determinant of EM transpose, but that is the same as determinant of E1 times determinant of E2 and so on up to determinant of EM. Again by the multiplicative property we get that is equal to determinant of EM, EM minus 1 and so on up to E1, and that is determinant of A. Now this remark, an important consequence of the above theorem is that determinants can be calculated by cofactor expansion along a column also. Moreover, elementary column operations can also be used for evaluating determinants. So we see that the concept of rank and elementary matrices are being used frequently. Let us now talk about Cramer's rule. This is extremely useful when we are trying to compute a solution of a system of linear equations. So, the assumption is A is an n cross n matrix over F. Ax equal to B is a system of linear equations. X stands for this column matrix x1, x2 and so on up to xn. The unknowns, and B is that column matrix B1, B2 and so on up to Bm. Now, if determinant of A is not 0, then this system of equations has a unique solution given by xi is equal to alpha I is equal to determinant of Ai over determinant of A for every I from 1 to n, where Ai denotes the matrix obtained by replacing the ith column of A by that column vector B. Proof: if determinant of A is not 0, then A is invertible, and therefore, it is clear that the system of equations Ax equal to B has a unique solution given by A inverse B. Now, let us denote the ith column of A by Ci, and let Xi denote the matrix obtained by replacing the ith column of the identity matrix I by X. Then Axi is the matrix whose jth column is Aej, but that is Cj, the jth column of A, if j is not I, and the ith column of Axi would be Ax, that is B. Therefore, this matrix Axi is precisely the matrix Ai, and it follows that determinant of Ai, that is determinant of Axi, that is determinant of A times determinant of Xi, and that is equal to determinant of A times Xi. This proves the theorem. We have learnt basic properties of the determinant function, and we have seen that both rank and elementary matrices have been used effectively, especially when we talked about invertibility of a matrix. Then we use the fact that it can be written as a product of elementary matrices, and if we said that it is not invertible, then we use the concept of rank. We said that then the rank is not the full rank. So these two concepts have been used on various occasions. Now it's time to characterize the determinant function, and what is interesting is that we will see that a multilinear function with some properties becomes the determinant function. In fact, that has to be the determinant function. And if you remember, we had talked about the area of the parallelogram in the real plane, and we had defined a function called delta, and the proof of that proposition was postponed. We said that after we do the classification, we would eventually complete the proof, and now it is going to be done after we classify the determinant function as a multilinear map. Suppose that A is an n cross n matrix over the field F with rows R1, R2 and so on up to Rn. Then we write A in this column form, where this R1, R2, Rn are the rows, which are in fact n tuples with entries from F. A function delta from MNF to F is called n linear or multilinear over the field F if it is linear in each row when the other rows are kept fixed. That is, for every scalar C and n tuples R1, R2 and so on, Ri dash and so on up to Rn, which are n tuples in Fn written in row form, then delta of R1 and so on, Ri plus C, Ri dash and so on Rn is equal to delta of R1, R2 and so on Rn plus C times delta of R1 etc., Ri dash etc. Rn. So, you can see that all the row vectors R1 and so on up to Ri minus 1 and then Ri plus 1 and so on up to Rn are kept fixed, and we are demanding that there should be additivity and homogeneity with respect to the ith spot, and that should happen for every I. So, it is separately linear for all the n spots or n linear or multilinear. The definition of n linearity of delta can be restated as follows. If we identify MNF with this Cartesian product of Fn, n copies of them, then this identification being this column R1, R2, Rn, where R1, R2, Rn are the rows of a matrix going to R1 transpose etc. up to Rn transpose. So, that what you see on the right hand side is an n tuple of vectors of Fn. So, up to this identification we can define delta from Fn Cartesian product dot 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 Cartesian product Fn to F is called n linear if it is separately linear in each variable. Some examples: the determinant function is an n linear function. We have already seen the determinant function as a function from MNF to F, and from the list of properties of the determinant function it follows that it is an n linear function. Next example, the trace function from MNF to F given by trace of A is not n linear. Next example, let us define this function delta j from MNF to F for a fixed j in between 1 and n to be delta j of A is equal to product of Aij where I is running from 1 to n. That means for a fixed j, this is the product of entries in the jth column of the matrix A, and this is an example of an n linear function. And the next example says that the function delta from MNF to F defined as delta of A is equal to product of I equal to 1 to n, that is the product of the diagonal entries of A is n linear. Definition: an n linear function delta from MNF to F is called alternating if delta of A is 0 whenever two adjacent rows of A are the same. and it is easy to prove the following theorem and its corollaries. The theorem says that let delta from MNF to F be an alternating n linear map. A is an n cross n matrix over F. If B is obtained from A by interchanging rows of A, then delta of B is equal to minus delta of A, and 2, if any two rows of A are identical, then delta of A is equal to 0. It is not difficult to prove this theorem, we just omit the proof here and let us see some corollaries of this theorem, and those will be extremely useful when we do the classification. Corollary: let delta from MNF to F be an alternating n linear function. Let A be an n cross n matrix over F. If B is obtained from A by adding a multiple of some row to another row, then delta of B is equal to delta of A. Next corollary says that let delta from MNF to F be an alternating n linear function. If A in MNF has rank less than n, then delta of A is 0. The third corollary, let delta from MNF to F be an alternating n linear function. Let E1, E2 alpha and E3 denote the elementary matrices of types 1, 2 and 3 respectively. Then delta E1 is minus delta I, delta E2 alpha is alpha delta I, and delta E3 is delta I. Therefore, delta E1 is determinant of E1, delta E2 alpha is determinant of E2 alpha, and delta E3 is determinant of E3. And a theorem, it says that let delta from MNF to F be an alternating n linear function such that delta of I is 1, then delta is multiplicative. Delta of AB is equal to delta of A times delta of B for every AB in MNF. Well, you can see that almost all the properties of the determinant function actually hold good for this function delta, which is an alternating n linear function, and also with the assumption delta I is equal to 1, we have the multiplicative property as well. Now we are in a position to state the characterization theorem, and it says that determinant is an alternating n linear function such that delta of I is 1. Proof: we follow the following steps to prove this theorem. First, if rank of A is less than n, then delta of A is 0, that we have already seen, and that is equal to determinant of A, because we know that if rank of A is less than n, then both determinant of A and delta of A are 0, and therefore they match. And if rank of A is equal to n, then we know that A is invertible. Once again, we write it as a product of elementary matrices. Let us say Jm, Jm minus 1 and so on up to J1, and then delta of A is delta of Jm and so on J1, and that is the same as delta of Jm times delta of Jm minus 1 and so on up to delta of J1, which is the same as determinant of Jm and so on up to determinant of J1. Determinant being multiplicative, we have determinant of Jm, Jm minus 1 and so on J1, that is determinant of A. This proves the theorem. We have seen determinant function, and when we listed down all the properties of the determinant function, we saw that a very important property it has is that it is a multilinear function. And then one of the properties says that when we interchange two rows, then a negative sign is introduced. And of course, determinant of the identity matrix is 1. So these are the three main properties which characterize the determinant function. And finally, what we have proved is, if we have a multilinear or n-linear function that is alternating, and if the value for the identity matrix is 1, then it is nothing but the determinant function. So this characterizes the determinant function completely, and going back to that statement what we made in the previous module when we talked about area of the parallelogram, we have also settled the proof of that proposition, where we had to find an expression for the area of the parallelogram. So that delta function which we had defined is nothing but the determinant.